So in the previous class, we have seen that the homojunction diode laser suffers from very poor electro-optic efficiency. That is because the confinement of light and the charge carriers is not possible in the vicinity of the junction. That increases the threshold current significantly high, the current that would be required the onset of lasing extremely high, and that does not allow operation of a homojunction laser in CW condition. Even in pulse condition, the operation is possible only when the device is cooled to liquid nitrogen temperature at 77 degrees Kelvin. That is simply because at such high threshold current operation, the dissipation of heat is significantly high. And the applications of such lasers is extremely difficult because wherever the laser has to go, it has to go with this baggage of liquid nitrogen cooling bath. And we also have just mentioned that this disadvantage can be overcome if by making use of a double heterojunction diode. Today we will go a little deeper and try to understand the underlying physics that makes confinement of both light and charge carrier possible within the junction layer of a double heterojunction diode laser. So, heterojunction diode laser. The limitations of homojunction lasers can be overcome if both the light and the current carriers are confined within the narrow zone of the junction laser, a seemingly uphill task. It is not surprising that the operation of a continuously working diode laser was realized at room temperature only more than half a decade after the discovery of lasing in a homojunction diode laser in the latter half of 1962. Nature was again kind here, as a material with higher band gap intrinsically possesses a lower refractive index. In this context, I will refer to an important work carried out by Trevor Morse, a British physicist, who was the first to connect the electronic and optical properties of a semiconductor by a rule that is now known as Morse rule and is given by band gap energy into refractive index is constant. So what does it say? Morse's rule. It says that the band gap of a semiconductor multiplied the product of band gap of a semiconductor and refractive index of that semiconductor is constant. So if we take two semiconductors, one is semiconductor A, the other is semiconductor B. So this Morse's rule says that band gap of semiconductor A multiplied by band gap of multiplied by refractive index of semiconductor A will be equal to band gap of semiconductor B multiplied by the refractive index of semiconductor B. So that means if band gap of semiconductor A is more than the band gap of semiconductor B, then refractive index of semiconductor A must be less than refractive index of semiconductor B. This is very important, and this was the key of the operation of heterojunction semiconductor. let us see how this has been exploited. And who was the first to exploit it? This advantage was exploited for the first time in 1968 by Herbert Kroemer, a German-American physicist, and George Alferov, a Soviet and Russian physicist, when they succeeded independently in the confinement of both light and current inside the junction. That means light and the charge carriers inside the junction. The conception of a novel heterojunction diode did the trick here. A masterstroke that killed two flies with one slap. Both the problems, that is confinement of light and confinement of charge carriers, could be solved just by one masterstroke, that is use of heterojunction diode. The room temperature operation of the CW diode laser, which was possible with this exploitation of this rule, eventually fetched Kroemer and Alferov the 2000 Physics Nobel Prize. So, in order to simplify the understanding of the physics of confinement, we first consider at this point a single heterojunction diode. So this is our single heterojunction diode, that is, one side is gallium arsenide, the other side suppose is gallium aluminum arsenide. So these two are two different semiconductor material. One has been doped to make it p-type and the other has been doped to make it n-type. So this is the junction where actually recombination will occur and light will be produced vicinity of this junction. So how the confinement will occur? You see, gallium aluminum arsenide has a higher band gap, is a higher band gap semiconductor compared to gallium arsenide. So these are the junctions. So then gallium aluminum arsenide has higher band gap. So this is the valence band and this is the conduction band. So the energy gap, band gap for gallium arsenide is more than the band gap for gallium aluminum arsenide is more than the band gap of gallium arsenide. This is the conduction band of gallium arsenide and this is the valence band of gallium. So this energy is less than this. So if the band gap of this is less than this, then according to Moses' rule, the refractive index of gallium, aluminum arsenide is less than refractive index of gallium arsenide. So now you see, if it is so, then the light that will be produced, so this side is more refractive index, this side is less refractive index. So if the light is produced just in the vicinity of this junction in this side, then this light, you know, when light travels, from high denser medium, that is from this side to this side, it can undergo total internal reflection. So the light will be blocked by this interface from this side. Similarly, this side has lower band gap than this side. Therefore, the electrons which travels from this side to this side, because this side band gap energy is more, so electrons energy will not be enough to move from this side to this side. Therefore, this interface, this junction will work as a barrier for both light, for penetration of light from this side to this side, as well as charge carrier from this side to this side. However, The same would not be true for the light. Light that will shine on this junction from this side, because this is of lower refractive index, so it won't be totally internal, it will not be undergo total internal reflection. So the light will actually refracted into the other side. Similarly, the charge carrier, this side is high band gap and this side is low band gap. Therefore, holes can actually cross over to this side. So the single heterojunction will, of course, allow partial confinement of light and partial confinement of charge carriers, not full. But this explains that how a heterojunction can offer confinement of both light and charge carriers, although partially if it is a single heterojunction. So then you see gallium arsenide is higher band gap semiconductor, and the electrons that are injected into the junction from inside lack energy to cross over into the gallium arsenide is a lower band gap. This situation is depicted in the middle base. Here, this situation has been depicted. This in turn results in an improved confinement of the charge carriers in a single heterojunction laser compared to a homojunction laser. It readily follows from Moses' rule that gallium arsenide, being a lower band gap material, will have a refractive index exceeding that of gallium aluminum arsenide. Consequently, the passage of light from gallium arsenide to gallium aluminum arsenide will be blocked, as the phenomena of total internal reflection will be operative here. The fact that I just explained. A single heterojunction laser thus allows only partial confinement of both current and light and is capable of operating in the pulsed mode at room temperature. And with this, although the operating efficiency, electro-optic efficiency is better, but even then it was unsuitable for continuous operation at room temperature. It worked at continuous operation at liquid nitrogen temperature, a step better compared to homojunction. So then we go over to double heterojunction and see how it makes it work beautifully. So now how do you make a double heterojunction laser? The confinement would be much better, but going for a double structure heterojunction. So how it is formed? You actually have a thin slice of intrinsic gallium arsenide semiconductor, which is sandwiched between p-type gallium aluminum arsenide and n-type gallium aluminum arsenide. That means this side is gallium aluminum arsenide, this side is gallium aluminum arsenide, and you dope it to form p-type and you dope it to form n-type. And between these two, you actually sandwich a thin layer of intrinsic gallium arsenide. So then you have two junctions. This is one heterojunction because the two sides, the two different semiconductors. This side is gallium arsenide and this side is gallium aluminum arsenide. And similarly, this is another junction, heterojunction, because this side is gallium arsenide and this side is gallium aluminum. So see now what happens. The light that will be created in this side, because this has higher band gap. So band gap of this gallium aluminum arsenide is more than band gap of gallium arsenide. So refractive index of this gallium arsenide will be more than refractive index of gallium aluminum arsenide. So light that would be produced here, this is high refractive index, this is low refractive index. So it will undergo total internal reflection. Similar to the light which will be produced here or shine onto this will also undergo total internal reflection. And therefore, light will be confined from both sides within this. Similarly, the charge carriers which has which will be easily diffuse, because this is high band gap, this is low band. So it will diffuse into this side. But from here it cannot go, because this is high band gap, this is low band. And same also would be true for this surface. So then you see this double heterojunction laser would work perfectly as far as confinement of both light as well as charge carriers are concerned. And if the charge carriers are very well confined here, then the chance that they will recombine and produce light would also be extremely high, and the produced light would be very well confined inside this. So you see, double heterojunction diode laser allows perfect confinement of both light as well as charge carriers. The double heterojunction diode laser is improved confinement of both current and light within the lasing volume, therefore ensures that the majority of the charge carriers recombine here and emit light. The threshold current for the onset of lasing is therefore remarkably less than that of the homojunction. This can be easily established by performing an experiment where you see the current has been plotted as a light intensity as a function of current has been plotted, but for both homojunction laser and heterojunction laser, you can clearly see that the threshold current for lasing for heterojunction laser is much less as compared to I threshold for heterojunction is much less compared to I threshold for homojunction. So this allows continuous operation of semiconductor laser at even room temperature, because at such low current, the dissipation of heat dissipation into the diode is much small. Therefore, it can be, even in room temperature, it is effectively becomes effectively cold, and no such liquid nitrogen bath cooling is required. So this results in significant improvement in the performance of the laser by establishing increased electro-optic efficiency and reduced heat dissipation. It is not therefore surprising that room temperature CW operation is readily achievable from a double heterojunction laser. As a matter of fact, the semiconductor laser of today are primarily based on such double heterostructure design of diodes. So with this understanding of homo and heterojunction diode lasers, we can now turn our attention on the role of cavity, how the different cavity can be designed for the operation of such diode. So we now basically explore the bearing of optical cavity on the overall performance of the heterojunction. So you see, this we have a heterojunction laser. So as you can see, this is the gallium arsenide intrinsic semiconductor, which is sandwiched between two other semiconductors, which is one side is P doped for P-type, generation of P-type semiconductor. The other side is doped to give N-type semiconductor, and between these two is sandwiched an intrinsic gallium arsenide. So this offers double heterojunction, and therefore there will be very efficient confinement of both charge carriers and light within this junction. So first, let us consider a longitudinal cavity laser and its advantage. So in longitudinal cavity laser, you see there are two advantages. The active length here equals the length of the junction layer. So this is the length of the junction layer, and this is the width of the junction. So if these two sides, these end faces, cleaved faces, of course, they have been cleaved to make them optically flat, these two faces will act as the two cavity layers. And therefore, the length of the active length is simply the length of the junction layer, because you have created population inversion in this. This is the active layer, and this also the length of the active length of the laser. And the two cleaved end facets with intrinsically high reflectivity, Fresnel reflectivity, that is because its refractive index is so high I have just explained, can perform the role of the cavity beams. A laser based on such a cavity would thus emit through its ends and is therefore termed as an edge emitting. The length and width of the N gallium arsenide substrate are approximately 300 and 200 micron. The length and width, so this is 300 micron and this is 200. The gallium arsenide junction layer is barely 0.1 to 0.1 micron thick. The thickness of this layer, that is this thickness, is barely 0.1 to 0.2 micron, 0.1 to 0.2 micron, extremely thick. Length is much more compared to the thickness, rightly so. The gallium arsenide junction layer is barely, as I said, 0.1 to 0.2 micron thick. The P-type aluminium gallium arsenide and N-type aluminium gallium arsenide layers lying on either side of the gallium arsenide constitute the PN junctions. This is P, this is N. This is the junction. The exceptionally thin active layer, lesser than the wavelength, makes the beam extremely divergent. You see, basically what happens is the electrical connection is taken by making a stripe electrode. So the current actually flows. If you look at the this active layer, so this is the, if I take a look at this, so this is like this. Its thickness is 0.1 micron. Length is 200 micron. And width, so length is 300 micron, width is 200 micron. And the current actually flows to this stripe, So the current flows like this. So you see, this is the lasing area. So if I would amplify and see it, so the area of the laser is this. Area of the laser is this. This is the thickness. So the area of the, the area over which the emission takes place is just this. So this is the thickness, which is 0.1 micrometer. And this is, of course, the width of this stripe, which may be 1 micron. So this is 0.1 micron, this is 1 micron. The beam emerges through this. This is the beam. So this is this area. So this exceptionally thin active layer, then the wavelength makes the beam extremely divergent. The beam is elliptic with its major axis lying along the thickness of the junction layer and the minor axis along its side. The strong diverging component intrinsic to this edge-emitting diode laser poses a major challenge. Therefore, because this side is much too short, therefore the beam will be elliptical. So the major axis lies along the thickness and the minor axis lies along the width, because the thickness is much too short compared to this side. This is this. So this strong diverging component intrinsic to edge emitting diode laser poses a major challenge. So what is the remedy? Remedy is to go for surface emitting diode laser. This limitation of the edge emitting lasers can be readily overcome by configuring the cavity in the transverse direction. So now It allows the advantage of greatly enlarging the emitting area of the laser. We can increase the emitting area of the laser. So now this is the layer, and so we are actually taking the beam out from this side. So lasing will occur transverse. So this way. This is the transverse cavity. So the lasing would occur over this. So popular as vertical cavity surface emitting laser, a beam with remarkably improved spatial quality that is both round and much less divergent emerged from such a laser. As can be readily appreciated, this advantage comes at the expense of the gain length, because gain length is just this, the thickness, which is barely a fraction of micrometer, as we said, 0.1 to 0.2 micrometer, equaling the thickness of the active layer. This greatly reduced active length can be offset by accordingly reducing the round trip cavity loss. So we'll have to reduce, now the active length has reduced. So in order to satisfy the condition of lasing, we'll have to reduce the transmission loss from the both ends. So we cannot use the Fresnel reflection from the both ends, no, as the cavity mirror. So we'll have to, the moderately high reflectivity that the semiconductor materials are known to possess and comes in handy for edge emitting lasers would not suffice there. So what do? The use of Bragg reflector, which can offer remarkably high reflectivity when appropriately designed, has emerged as the most attractive choice to effect lasing in this vertical cavity laser. The Bragg reflector essentially is a mirror structure which consists of a stack of alternating high and low refractive index layer of two different optical materials, as can be seen here. There are alternating refractive index optical material which are placed on either side of this active layer. This offers a reflectivity of 95%, which can work as a output mirror, and the rear mirror has a reflectivity of about 99%. Almost it works like a 100% reflective. So this works as a rear mirror, and the top electrode is made annular, as you can see, to allow emergence of the low divergence circular output beam. The output beam emerges through this. Such lasers, DC ACLs, are inherently low power devices and usually generate less power than edge emitting lasers, simply because its active length is so much less, as the useful active volume where recombination of charged particle takes place is much too small. Actually, it's just, this is the active layer, so the active volume is very, very small, tiny volume. This is just the volume over which the lasing takes place. That basically makes it very low power laser. These lasers with their very low lasing current threshold and satisfactory beam quality are therefore an attractive choice for low power application. However, the tiny physical size of the active layer in a diode laser essentially limits its power generation capability to a modest level, which may be adequate for certain specific applications. However, for applications requiring high power, such as pumping high power lasers of a variety of material processing or medical application, power scaling is possible by combining the output of many single emitter devices. Two ways they can be combined. The number of diodes to be added depends on the requirement of power, and they can be stacked in a linear array, often called a diode bar. That means you can actually combine many such emitters and make it, which is called a diode bar, which can raise the power from watt to several hundred watts, such diode bars. And to meet the increasing demand of power, the diode bars can be stacked side by side as well as atop each other, forming a regular matrix of emitters with the capability of generating continuous power exceeding even kilowatt. So for that, you actually place diode bars either side by side or one atop the other. This can readily take the total power capability exceeding even kilowatts. Needless to say, provisions of adequate cooling by way of fabricating microchannels within the entire structure is prerequisite for the working of such high-powered devices called diode array. So it brings this course to an end. Over the first few weeks of this course, we have introduced to you the basic concepts of laser at an elementary level. You have studied spontaneous emission, stimulated emission, cavity, population inversion, and many more. You also now know that the integration of a population inverted medium with cavity is the key to making a laser. Majority of the course aimed at familiarizing you with the principle of working of a variety of important lasers that can be categorized as gas, liquid, and solid state lasers. We have chosen one or two important lasers from each of these categories for this exercise. However, there exists a few specific lasers that cannot be categorized in any of these three types, namely gas, liquid, and solid state lasers. But nevertheless, they profoundly impact our day-to-day life. These lasers have been addressed individually, and they include excimer, chemical, gas dynamic, fiber, semiconductor. We will be extremely happy if you have found this course useful and interesting. My team members, Dr. Padma Nilaya and Miss Tania Singh, join me in profusely thanking you for having chosen this course. I show here a list of books that you may find useful for this course. Most of these books actually follow an intuitive approach, the same approach that we also have adopted during this entire course. Of course, the first book in this list, namely Concept of Modern Physics, written by Arthur Baeser, actually provides some precursory knowledge that is essential to understanding the working of lasers. From this list, I would like to single out this book entitled A Beginner's Guide to Lasers and Their Application, not because it is written by me, but because it is one of a kind book, although written for non-experts, but it doesn't compromise the technical depth or scientific accuracy. It of course follows an intuitive approach, avoiding use of complex mathematical jargon, and most importantly, lucidity of the text, clarity of illustrations, and anecdotes picked from history are what make this one-of-a-kind book stand tall among the rest. Well, thank you very much.